right?
Let's pick up where we left off yesterday. So we got Pi Day tomorrow. I'm going to carve out a day, no pun intended, for Pi Day tomorrow. Give you guys I'll give you a work day on Friday, how about? I mean our Friday senior day.
Yeah.
Give you a chance to make up tests and things. So today I want to cover some things. So we talked yesterday about concavity at the end of the period. Right? We went through some sample problems, and at the end we started talking about, we took like the last 10 minutes to talk about concavity. So let's kind of review what we talked about. So we said that concavity is now we got to be careful with this, right? We got to make sure we understand these relationships well. So let's get everybody, close all these things up and get with me here. This is big. You don't want to miss this. We know that when we're talking about a function, the first derivative deals with slope, right? When the first derivative is positive, the function is increasing. We get a positive slope. Where the first derivative is negative, we get a decreasing function, negative slope. We know from our discussions of the first derivative test that we can look for extrema to be at the places where we get zeros of the first derivative or places where it's undefined, places where we could potentially transition from positive to negative. Like, for example, we know that a relative maximum or a peak is a transition from a positive first derivative to a second first derivative. And that's not hard for us to conceptualize. Maybe it takes a little bit of practice, but we can kind of get the hang of that pretty easily. And then a relative minimum would be a transition from decreasing to increasing, right? So we can look at a graph, and you can pretty easily tell me the intervals on which the function is increasing or decreasing. You might remember back in Algebra 2, for reasons unbeknownst to you at the time, we actually spent a little time kind of getting you acclimatized, thinking about that stuff, right? Okay, now we're going to make the jump to the graphical manifestation of the second derivative. How does it, what is what's the impact of a function's second derivative on its graph? Okay, and that's what we started to talk about yesterday, right? Just like the first derivative, f prime, is the rate of change of the function, the rate of change of y, right, which means slope. The second derivative is the rate of change of the first derivative. So it's the rate of change of slope, right? Which is that's a harder thing to get a handle on, I think, conceptually. So what we found was that if the slope is changing in a negative way as we move to the right, if the rate of change of the slope is negative, then every step we take to the right, the slope should get a little bit more negative, right? So here's an example of that. If we drag, that's not an example of that. That's a fixed picture, isn't it? If I were to look at the slope right here, I would have a fairly steep tangent line, right? If I scoot to the right a little bit, it's going to be a little less steep, Now it's 0. Over here, it's becoming more negative and more negative and more negative. And so that gives us the characteristic, this part right here of the graph, everything to the left of that dashed line. It's probably they're fixing the home. So everything to the left of that dashed line, we can sort of see. Those are the places where, as the ant moves to the right, the slope is getting more negative. It's less. As I move to the right, it's less than it was to the left, correct? At this point, right about there, things start to switch. From this point forward, as the ant moves to the right, now the slope starts to get less negative. It moves over a little bit more, it's even less negative. And then it's 0, and then it's positive, and then increasingly positive, right? So everything over here is a place where the rate of change of the first derivative is negative. Steps to the right mean a more negative or a lesser first derivative. Everything to the right is going to be a region where steps to the right give us an increasingly positive derivative. That gives us a characteristic shape, though, right? We know that the word that we apply to this in math is concavity. So a place where the second derivative is negative, where the rate of change of the first derivative is negative, always ends up being a concave down region of the function, right? What are the hallmarks of that? Well, we can easily test that graphically, and you can see that one way to think about it is downward concavity means the function tends to shed water if it's raining on the function, right, or snowing. So we also can see that places where it's concave down, if I draw a tangent line, the tangent line is going to sit on top of the curve, right? Places where the function is concave up, on the other hand, are places where the tangent line sits below the curve, right? So it tends to catch water. It's cup-shaped up or bowl-shaped up, right? So what's the big deal? Well, concavity is a big deal. Concavity is another one of those features when we analyze functions, and the functions don't have to be just mathematical functions. If we talk about the concavity of a profit function, like if you're in economics, it means something, right? Having a positive concavity means something to a quantitative economist. So we want to know about just the characteristic concavity of a function, but we also want to know, we can use that for other purposes. Today we're going to start talking about inflection points. So places where we transition between, say in this case, negative to positive concavity, we call those places inflection points. Okay, just like we would say the transition point of the first derivative from positive to negative is an extremum, the transition point of the second derivative from negative to positive or positive to negative, doesn't matter. If you're changing signs, it's an inflection point. Okay? So let's label that. Okay, and a good definition of an inflection point is this. Okay? This is a concept, and it's amazing how much of this stuff in calculus is just misunderstood. And oftentimes it's just taught incorrectly, or you'll even see it in textbooks where it's strictly speaking, it's just not correct. Like Khan Academy, which is awesome. The guy does a great job, but like he teaches a lesson on inflection points where he makes a mistake. And a lot of textbooks do too. There's a little bit of ambiguity in how you define this, but this really is the best definition. Okay, and I'm not going to get into this today. We're just introducing this today. We'll come back next week, and we'll look at a couple of specific examples where it's sometimes there's a problem with how textbooks cover it, where it's not done. There's some inconsistencies in the way it's taught, or the way it's shown in textbooks. So I want you to see, at least in my opinion, I mean, other people might dispute this, but I feel pretty strongly that this is the best way to do it. Okay? So it's a point where the graph of a function, where the concavity changes. That's the main part. But here's the part that I think is also critical that sometimes gets overlooked. Really, an inflection point, as we're going to come to discover when we talk more about this, really only makes a lot of sense and is really only useful if it's a place where the graph of a function has a tangent point. So it couldn't be a place where there's, for example, a sharp corner on a graph. That really wouldn't make sense for us to think about as a point of inflection. Okay. We'll come back to that later, though. All right, so I don't know if this is worth messing with today or not. I built this little thing in Desmos, and I guess we'll see. We'll see how it works. I don't want to spend a lot of time with it, but I spent time on it, so let's at least try it out. Okay, so here all I've got here is I've got a relationship between a function, its first derivative, and its second derivative. Well, you tell me, which one do you think is, of those, blue, green, or red, which one is probably the function? Which one is probably the first derivative? Which one is probably the second derivative? So the green's the function, good. So we can call that, let's call that F, yeah. Oops, that's what we want right there. There we go. Okay, so the green one we'll call F. The red one is F prime. And the blue one is double prime, right? That makes sense, doesn't it? We can look at it in either direction, too. And this is something I want you guys to kind of make sure you're feeling comfortable with this. If I gave you the green one and I said, graph the derivatives, the red one makes sense, doesn't it? Shape makes sense. And this goes back, we discussed this a long time ago. Because here's a place where we get a horizontal tangent, so the slope has to be 0. So the value of the red graph has to be at 0, right? So that's its x-intercept. To the right of 0, the slope is positive and increasing, so the value of the derivative function is positive and increasing, right? The slope of the green function to the left of 0 is increasingly negative as you go to the left, right? So here's the value of the red derivative function is increasingly negative. Okay, the second derivative is to the first derivative exactly as the first derivative is to the function, right? If we're looking at graphs. the graph of the first derivative, the red function, its slope is equivalent to the value of the second derivative. And that's how we talked about it previously, going clear back, months ago. We'd already mentioned this, right? So the red first derivative function, the slope is constant and positive, agreed? Just a line with a positive slope. So the value of the blue second derivative function must be constant and positive. Makes sense. So now the challenge is, one of many challenges for you, is to see if you can bridge that gap a little bit. See if you can jump right from green to blue. Okay? Right? If you look at this just looks probably like some kind of parabola, right? Some kind of quadratic function. Would you agree? And I would say you can't necessarily jump to the exact shape of the blue graph, because it's really hard to tell if the concavity is changing, honestly. But can you see that that this is consistent? The blue and the green graphs are consistent. The green graph appears to be concave up everywhere, doesn't it? The part we can see is, right? It's all bowl-shaped up. Any place where we add a tangent line, the tangent line is always going to sit below the graph any place, right? So we can see that it's always going to be concave up. And so it makes sense that we get a constant positive, or at least it's always positive at the very least. Could we flip this around? Could we start with the blue and work our way backwards? Like if we said, for example, we started with the blue and said, that's the graph of the second derivative. Could we come up with reasonable graphs of the other functions, the first derivative and the actual function f, right? Well, what's this telling us? That if we know that the second derivative is constant and positive, then we must know that we can pretty easily see that the first derivative has to have a constant positive slope, so we can get a line like the red line. Is the red line the only representative line we could pick?
No.
Could be any line with that slope, couldn't it? Right? I could take this same line and graph it, and this is something we'll get to, in Unit 4 a little bit more than we do this unit, but I want you to start thinking about this a little bit. Yes?
Wouldn't we be able to know that the red line is going to be not moved over on the graph at all because it's the first derivative or something?
What do you mean moved over?
Like, it's not going to be shifted to the right, left, up, or down because it's the first derivative.
Okay, but here, maybe this helps. Let me do this. What if we took this one out of the picture, right? What if we took, so all we know is that the blue function is the second derivative, right?
Yes.
That version of the red line is a reasonable first derivative, but so is this one. It's too far up. Let's make it, right?
But we know it's the first derivative, right?
Mm-hmm.
Which means that's gonna, yes, that's reasonable. That has to, it work for being the first derivative of the blue line, but it won't work for being the derivative of the green line.
You're right, but we don't have the green function there yet. See what I'm saying?
But we know that the red line's not going to be shifted up, don't we?
Mm-mm. No, we don't. So make sure everyone understands the point we're making. If we're just, all we know, if all I'm giving you, if we're doing this in reverse order, and this is a pretty important point in calculus, if all I tell you is that the second derivative of my function has the graph, the blue graph, it's a constant positive, there are an infinite number of first derivative graphs that would correspond to that. Anything that has a slope of 1, any line with a slope of 1 is going to work, isn't it? Because the slope is constant and 1 everywhere. See what I'm saying? Everybody get that? Okay, so now that's different than if we were to, what we did before. When we went the other direction with this, let's get rid of that thing. Oh, man, I can't see that. There we go. Okay, so if we started with the green function and we didn't have any of the other stuff, there is no freedom, is there? Right? And I think that's the point Elton's making. There's no freedom because we know that the red line has to have a value of 0 where? At 0, right? We don't have it, there's no wiggle room. It has to be that graph, right? Everybody see that? Okay, but if we're going the other direction, that's not the case. If I know if I'm given the second derivative first, then the first derivative, all we know is it has to have a slope of 1, right? What does the function look like? Well, all we know here is that the slope of the graph, of the first derivative graph, is increasing and positive, right? Does that make sense? It has to have a horizontal tangent at 0. Okay, so we can't slide it horizontally, but this would work, wouldn't it, if I did that works, doesn't it? Right? The vertex doesn't have to be at the origin, does it? All we know is that because the value of the derivative is 0 there, right? This is the point 0, 0, and that's the slope of the graph is 0, right? All that tells us is that we have to have a horizontal tangent here. The whole thing could be slid up anywhere we want to or slid down anywhere we want to. You get that? Okay? That's an important point that we'll come back to again in Unit 4, and we'll talk about in a lot more detail. Okay? All right. Okay, let's change things up a little bit before we move on. What if I made this cubic? Oops. Does that make sense? So once again, we're starting with the green function. The green function is the function, the red function is the derivative. Makes sense, right? We know that we get a horizontal tangent at 0, so the value of the red graph has to be 0, has to go to the origin is 0. To the right, it's increasingly positive. To the left, it's increasingly negative. And then the derivative of the red function is going to give us, we have a 0 derivative at 0, horizontal tangent. It's increasingly positive to the right, increasingly negative to the left. I think I said that backwards, didn't I? The green one is increasingly positive to the left, not negative. So the red's parabolic, right? Does that make sense? Okay. One last thing. I think I had this set up. Yeah, how about that? Okay. Here's the one I really wanted to get to. So once again, this is F, this is F prime, F double prime. Okay, does that make sense? The green one has horizontal tangents there and there, so those must be places where the red function has a value of 0, right? Every place to the right of this, the green is increasingly positive. Between these two x values, the green function is most negative in the middle, but it's always negative. And then to the left of that maximum, the green function is increasingly positive, right? The slope is, okay? I should say the slope of the green function is. How about the blue function? Notice that the blue function, here's the stuff we're talking about today. The blue function only has 1, 0, and it's right there. How come? Yeah, that's the one place where the function transitions its concavity from being negative on the left to positive on the right. This is bowl-shaped down over here. This is bowl-shaped up over here, right? So that tells us that F double prime is less than 0 over here. And then over here, F double prime is greater than 0. So that's our inflection point. Right? Do we see that? Okay? All right, so let's practice this a little bit. These are the kinds of problems I gave you on the 3.4 practice 1. It's not really, you have to do any calculus other than just being able to look at the graphs and figure out what's going on with the derivatives on the graphs. How about this one? Okay. Okay, so all they're asking you to do here, there's a whole bunch of graphs on this one. There's 1, 2, 3, 4, 5, 6, 7, 8 situations where you've got to match up the behavior of the of the function, first derivative, and second derivative on the closed interval from A to B. So it's telling us that, for example, for graph A, the first derivative is positive on this interval. The function is positive, the first derivative is negative, and the second derivative is positive. So what kind of shape is that going to fill? Each one of those communicates something to us. What does it mean that the function is positive on the interval from A to B? So what's that look like graphically? It's above the x-axis, right? That makes sense? So that's telling us above the x-axis. What does it mean that the first derivative is negative everywhere on the interval from A to B? Slope's negative, so the function is decreasing, right? What does it mean that the second derivative is positive? Say it again. Okay, but what's it look like in terms of the graph? What's that telling us? Positive concavity, so bowl shaped up, right? So which one of those graphs for part A is going to do that? Well, I guess you can see it's that one, right? It's above, from A to B, it's in quadrant 1, it's above the x-axis. It's decreasing on the entire function between A and B, and it's concave up, so it's got to be that one, doesn't it? Okay, what's this one going to look like? Let's look at B. I'd do all of these, but let's do a few. F is positive, what's that telling us? Above the x-axis. F prime is negative. Decreasing. F double prime is negative. Negative concavity. Okay, so that would be C. Okay, right there, wouldn't it? Right? Above the x-axis, ants walking downhill, and it's bowl-shaped down. Right? Tangent lines. The other test we could always use, tangent lines sit above the curve. Sit on the curve if it's concave down. Okay, we're not going to do all these, but maybe let's look at one more. How about? So what about, just look at C, I guess. So if we get the function is negative and both the first and second derivatives are positive, it's going to be below the x-axis, increasing function, walking uphill, and concave up. So it's got to be that one, doesn't it? Yep. Right, you get the idea. Okay, how about this guy? Okay, so I'm going to skip this one. Well, I have another one just like that. Okay, how about something like this? So this time they're giving us the second derivative and the first derivative. Everybody on your own, just take out your scratch paper and just see if you can make a quick sketch of this. So graph a possible function f. Now it's not unique. There's an infinite number of different answers, but one that meets those criteria, that's consistent with the blue first derivative and the red second derivative. And what you want to think about is what are the key points that this graph is communicating to you? Key points on F that are communicated by the graphs of its first and second derivatives. Okay? What do you think? What do you say? Okay, as we're moving from negative infinity now, what's probably the first place up there where we get a point that's important on the blue first derivative graph?
Crosses the x-axis.
Okay, so right there. Gabe, what's that telling us? Right there. First derivative is 0 there. What's that telling us? Okay, it's got a horizontal tangent, right? Got a horizontal tangent because the slope is 0. So in this case, the horizontal tangent is a transition. What is that going to correspond to, a relative max or a relative min? It could be a maximum. How come? Positive to negative. So we get a positive first derivative on that side and a negative on that side. So where do you draw it? That's up to you. I mean, we don't know exactly. There's no one right answer. But we know that we're going to get something like, there's our horizontal tangent. So the graph's going to do maybe something like that, right? Okay, what's going on there? Okay, another horizontal tangent. This one's going to be a minimum. Good. Good. So we got a 0. We got a horizontal tangent. We know we're going from decreasing to increasing. So down here somewhere, we're going to get that behavior, right? And then we get another one over here, don't we? And this is going to be another case where we're going from positive to negative. So somewhere over here, we're going to get another maximum. Okay, so there's the information we get from the first derivative graph. What are some important places on the red graph? Like what's this going to be, for example? Okay, so that's where the second derivative has a value of 0. So it's transitioning from negative to positive. So now think about it. That's the one that's harder to conceptualize. From the second derivative, which is what? Graphically. Not slope, what's the word we use? Concavity. So the concavity is going from negative, which is what kind of concavity? Down. To positive, which is up, right? So that's got to be at that x value right there, right? So what's that look like then? That's going to have to be the place where we're going to transition from bowl-shaped down to bowl-shaped up. So right there is where, see what I'm saying? It goes from shedding water to catching water, and then we're going to get the same thing happening right here, aren't we? Right? So here's another place where we're going to have a change in concavity, right? Something like that. Right, there's an example of something that would work. Okay, so now here's the next challenge, and we don't have a ton of time, but let's see if we can make another connection. Can you tell me that for each of these extrema, important places to look, right? For each of those extrema, can you relate the red second derivative graph to the shape of the curve? What do you think? You have an idea?
Yeah. The number of zeros on the second derivative of the function is going to be one less than the number of zeros on the first.
Okay, yeah, that's true, but that's way more complicated than what I'm looking for. I'm just looking for this. Now, let me phrase it a different way. So let's say that we don't want to use the first derivative test. And think what the first derivative test is. The first derivative test, that's how we look for relative extrema, by finding critical numbers that are transitions in the first derivative's sign, right? So we knew this was a maximum because it was a point of transition from negative first derivative to positive, or from positive first derivative to negative first derivative, right? Let's not do that. Let's do something else. Let's only use the first derivative to point out the places where we have a horizontal tangent, right? So the fact that the y-coordinate of that point right there is 0 is just telling us that this is a horizontal tangent, okay? Now let's couple that with the fact that if I continue this line down, it's telling us that the value of the second derivative is negative at that point. Everybody agree? If I look at this point on the second derivative function, I'm going to get some x value. All I know that I'm getting for a y value is a negative number for my second derivative function. So if I know I've got a horizontal tangent to the curve plus a negative second derivative, what does that have to be? It's got to be a maximum, doesn't it? Right? If the function is concave down at a place where it has a horizontal tangent, doesn't that imply that that has to be a maximum? That's the second derivative test right there. Graphically, that's the second derivative test. Now, we'll see this on our tables. It's pretty easy to represent on our tables, but that's what it means graphically, right? Let's apply the same thing here. At this point right here, we know we have a 0 first derivative, which means we have to have a horizontal tangent line, right? At that point, though, notice that the value of the second derivative is positive. So we've got a horizontal tangent coupled with a positive concavity. Doesn't that mean it has to sit on the tangent line, right? The tangent line has to be below the curve where the concavity is positive, so that means a minimum, right? Relative minimum. And then once again over here, the red function's off the graph, but you get the idea. Where we have a 0 first derivative, that means a horizontal tangent line. Clearly the second derivative is very negative, so this is going to be concave down, right? Get the idea, okay? All right. We'll come back to this later. We'll do that now. Okay, so let's actually put this to work in a table, and this is where we'll end up. Let's do one problem for today. So let's do all that stuff we did graphically. Let's start with the function this time and build a table that's going to allow us to come up with a representation of the graph. Same information, essentially. All right. So here's our function. In order, we want to find all relative extrema. Okay, so relative maxima, local or relative, same thing, maxima and minima. And while we're at it, let's go ahead and let's find all the inflection points too. We'll add that as kind of a bonus, right? So what are we going to need to do with our function to find the critical numbers, first of all? Take a derivative. Okay, so we'll take the first derivative. This is a polynomial, so it's a super easy derivative. We can just differentiate term by term. What do we get for the first term?
Negative 9x squared minus 18x.
Okay, so there's the first derivative, right? So is f prime undefined anywhere? No, it's a polynomial. So we know f prime equals 0 when x equals what? So we could, I guess we'd want to factor this, wouldn't we? Right? So we'd end up with, I could factor out a negative 9x, everybody agree? Leaving me with what?
X plus 2.
Okay? So if there's our first derivative, when is that 0? When x equals
0 and negative 2.
0 or negative 2, right? The zeros, if I set this thing equal to 0, everybody see those are the values I get? Okay? Okay, while we're at it, let's keep going, because we're going to want the second derivative also, right? We're going to talk about concavity here. So the second derivative, and we want to go from here, right? We want to ignore that step. We just want to differentiate this as a polynomial because it's so easy. Derivative of negative 9x squared is,
-18x minus 18.
okay? And so that's nowhere undefined, right? But it is equal to 0 where? F double prime equals 0 when x equals, okay, make sense? And if we wanted to, we could factor out a negative 18, leaving us with x plus 1, and if I set it equal to 0, I get negative 1, right? Okay, now let's add that stuff to our table. This is so cool. Make sure, I mean, I'll publish these notes, but this is like one of my favorite things to teach. I just love it. So, get our x-axis, we got function, we got the first derivative, and finally we get to add that second derivative row. And as a general rule, well, I'll say this again, but the further you can work down the table, the more efficiently you work in this table, okay? So we want to try to, we'll avoid, whenever possible, we'll avoid the first derivative test because it requires more work, and we'll see that. You have to do all these extra test points that you don't need to do with the second derivative test. So it's easier to work further down the table. So the domain of this function is what? Already. Right, so our domain, we add that. And what are our critical numbers? Well, we get first derivative critical numbers, right, where the first derivative is 0, and that's at x equals 0 and x equals negative 2. Okay, those are places where the first derivative is 0, right? We won't even add the second derivative stuff yet. What does that tell us so far? I've got this function that is defined everywhere. If the first derivative is 0, I'm going to color code this so we can see these connections. So if the first derivative is 0, then that tells us horizontal tangent, exactly, right? Okay, let's look at the second derivative row now. If f prime of x is equal to, we've got it in factored form right here, don't we? Right? So f prime of x equals negative 18 times x plus 1. You could use either row, but when it's in factored form, it's really easy. All we need to know, if we want to apply the second derivative test, is what's the sign of the second derivative at each of these first derivative critical numbers, right? What's the sign of f double prime when x is negative 2? F double prime of negative 2 is going to give us negative times negative is positive, right? Okay, what did we just say on that last graph? If we have a horizontal tangent, if we have a 0 first derivative and the concavity is positive, what's that have to be? It's got to be a minimum, right? It's opening up. So that's what the positive concavity tells us, right? Okay, what about over here? What if we try f double prime of 0? What's that give us? So we're going to get negative times positive equals negative. So we got a horizontal tangent, negative concavity. We know what those are, right? You got a relative minimum and a relative maximum. Isn't that better? Now, what if we'd applied the first derivative test? If we wanted to apply the first derivative test to figure out what these were, I would have had to have chosen test points in between, and that's extra work. You see how that's harder to do? Okay? So while we're at it, I'll show you how easy it is to find inflection points, right? Inflection points have to be places where the concavity is changing, where the sign of the second derivative is changing. But what are the only places where the concavity of a function, where the sign of a function can change? Where it's 0, or in some weird cases, it could even be where it's undefined, right? But if we look at our second derivative, the second derivative is everywhere defined, but the second derivative only equals 0 at -1, right? And there we have it, f double prime equals 0 when x equals -1, okay? So we'll add this other point up here. When x equals -1, we get a 0 second derivative, and all the work is already done. There's nothing else to do. There's the only transitional point of the potential transitional point of the second derivative, and to the left of that it's positive, to the right it's negative. So what is that? It's got to be an inflection point. What's our definition of an inflection point? It's a place where the concavity switches, right? So that's it. So then we can also add right here, we know that this is going to be an inflection point, and that gives us a lot of key information, right? That tells, I mean, we're about out of time, but all we'd have to do to really anchor this thing and make it a solid graph, the only other thing we might want to do is just figure out maybe what are the y-coordinates of those points, and then we've got 3 key points that anchor all this behavior. We could do a pretty good sketch of that graph, couldn't we? Right. Yes, sir.
So you said it's a potential transition point. What is taken with it not?
Okay, this is the first example we'll look at next time we talk about this stuff. Because it could be that we get a 0 of the second derivative here, but it's positive on this side and positive on this side, in which case it would not be an inflection point.
What would it be?
It would end up being actually a minimum. But we'll talk about why that is. I'll tell you that now, but we got to discuss it a little bit so it really makes sense.
Be a minimum?
Be a minimum.
Possible both sides?
Yeah, because, well, here's my quick explanation. If the function is concave up everywhere for all values of x less than -1, and it's concave up for all values of x greater than -1, you see that that's really, what's the implication there? Concavity or slope or any kind of these functional behaviors all depend on the relationship between this point and the points next to it, right? What does it mean? I mean, how could you have a single point that has a concavity? You can't, right? You can only discuss the concavity of a function when you compare the behavior of the function there to its neighbors. Well, if it's positive concavity for all values greater than -1 and all values, or less than -1, and all values greater than -1, doesn't that mean it's concave at -1 too, effectively? Right? See what I'm saying? There's another way to look at that, though, that shows it using first derivative. They're totally, and this part's really cool.
So if points on both sides were negative, would it be the maximum?
It'd be maximum. Yeah. Yep.